Welcome to this video. Today we will have a short look at channel measurements in the D-band. In 6G there are many new technology components, and one of these technology components is the terahertz frequency range. And as in 5G, the motivation is the same. In order to reach higher data rates and lower latencies, it is necessary to go to higher frequencies. And for 6G, the area beyond 100 gigahertz is very interesting and is a topic research, namely the D-band and the HJ band in the 300 gigahertz region. So as in 5G, also in 6G, one of the first steps of the standardization will be the definition of the new physical layer. And the first part is to understand better the propagation characteristics in this frequency region. And for this reason also, next year, the WRC, the World Radio Conferences in 2023, is kind of a target of many research labs because they want to show the feasibility of terahertz communication. In today's video, we would like to give you a short demonstration of how to measure the channel characteristics in the D-band and give you example measurements. In the next part, I would like to give you a short overview of the measurement setup. So in time domain channel sounding, which we will show today, the concept is very similar to sonar actually, for example in submarine. In sonar you have a very short pulse at t equals 0, and then look at the reflections, the acoustic reflections from the environment, which gives you a picture. And here we have an electromagnetic wave and look at the reflection from the environment. This gives you a picture of the environment and, let's say, the propagation characteristics. Here we have the signal generator. It's an SMW, and which creates the sequence. So we use a Frank-Jarlov-2 sequence. It creates a signal 4 gigahertz bandwidth. So here we have two times 2 gigahertz outputs. It's combined and then fed to the up converter. So this is the external front end, FE170, which covers the D-band from 110 to 170 gigahertz. Today's frequency is 160 gigahertz. Then we have an amplifier stage and a horn antenna. And here on the other side, we have the receiver. Again, the front end, external front end, covering the D-band. In this case, we don't have a horn antenna because we want to capture reflections from all areas. Yeah? So it has a very wide opening angle. Then it's down converted, going to the FSW signal and spectrum analyzer. And then the IQ data is then fed into the PC and processed to display the channel impulse response. So let's start the measurement. So here we see the channel impulse response. You see we have a very good time resolution because we have 4 gigahertz bandwidth, which means it's 1 over the bandwidth is the time resolution, which means it's 0.25 nanoseconds. And we see, of course, the first line of sight peak, which is the strongest peak, but also other reflections. And note, please, the dynamic range is very good. So let's compare this then with another measurement where we have a larger distance between the transmitter and receiver. Okay, so now let's have a look at our second measurement. We increase the distance between the transmitter and the receiver to approximately 50 meters now. And in the measurement itself, you can see that, again, the channel impulse response and the first line of sight peak is, of course, delayed compared to the previous measurement. And you see other reflection from the environment. So today you could get an impression how to perform channel measurements in the frequency range beyond 100 gigahertz, in particular the D-band. This is just the starting point. So now we plan to further extend these measurements in different environments, indoor, outdoor, also industrial environments, also at higher frequencies beyond the D-band, for example, the 300 gigahertz region. So with all these measurements, in the end, these are just puzzle pieces. One needs to combine them in order to define and develop a channel model, which then allows you to develop the physical layer for 6G.